MIPI standard touch. Here's James.
All right, thank you, everyone. It's my great pleasure to be here. It's rare that a brand new standard gets to be introduced. The MIPI touch standard is completely new. It's now about to be in final draft, and it's going to be released this year. I just want to first thank I'm the lead editor. I'd like to thank some of the lead contributors. Intel, Nobu Suzuki, Samsung, Frank Cito, and Dale Stolitzka, Huawei, Kenneth Ma, Synaptics, Jeff Lucans, and of course from Qualcomm, myself and David Johnson worked on the standard. So this brand new standard is not just touch with one command, one standard. It's actually a variety of standards. This is a new trend because the standards are getting so technically complex. We're starting to leverage a lot of the MIPI ecosystem, so I'll talk about that. The architectures that are supported by these 4 different standards are quite flexible. Number 3 here, the stack up leads to a very nice command module. Essentially, what we are trying to do is give something to the engineers that's easy to use and solve some basic problems for touch and sensors in general. I'm essentially today going to focus on the MIPI touch command set, but I will talk about some of the other details. If you walk away from this meeting, understand the key latency proposal that we have. That is the key goal of my talk. There are many slides in the deck. It's the end of a long day session, and I just would like to focus our group on 2 or 3 key topics. I invite you to please read the entire presentation, the technical details, but please remember, this is not the technical standard. You must get the final standard. Please do not start designing products based on a series of slides. You must get the actual technical standards. So where do we sit today with touch and sensors in general? Essentially, we found after 2 years of effort that this is not a standardized marketplace. We see touch sensors beginning to really propagate. They're going all over the place for XR, automotive, and a variety of different applications we've talked about earlier today. But they're not standardized. And the current legacy interconnects and link layers have lasted a very long time. I2C is nearly 40 years old. And there are new problems and challenges that need to be addressed with a new MIPI touch standard. Number 1 among them is power. A lot of these interfaces have been designed for 40 years and do not optimize for power. Number 2, 40 years ago, pins were expensive, but not nearly as expensive as they've become in very deep submicron technologies. So the idea of reducing pins has taken on a greater urgency while reducing power, while requiring lower latency and higher throughput. So again, the classic engineering challenge of trying to make everything better. And let's talk about how to do that. So the new touch standard that we're introducing today has many different layers to it. The top layer is called the MIPI touch command specification. That top level MIPI MTCS, or MTCS for short, is completely PHY agnostic. The idea is that this command layer will work on multiple MIPI PHYs. Now today I will focus on I3C, which is the latest standard to come out, but we have visions for the MTCS to work across multiple patterns. We're going to leverage that again. We have between the MIPI layer and the actual base layer is an adaptation layer for I3C, codenamed Alice, or ALI3C. We just call it Alice for short. I'll talk about that. The idea of Alice is that it provides an adaptation layer between the physical interface at the bottom and the high-level touch command set. Again, please be aware this is a trend in our industry, and so this first specification we believe will set the trend for the next few years and new types of touch and MIPI sensor standards. The idea of the adaptation layer is to explain to engineers what specific features at the low link layer and the PHY layer will be required. And I will spend the majority of the talk on that, specifically in-band interrupts and low latency. So let's talk about something we've all learned in school. This has been traditional and probably is in every single chip that we all work on. This is the classic interrupt cycle. You get an out-of-band interrupt on a pin that's probably running in the kilohertz, interrupting your main CPU or your sensor. And this interrupt pin asserts a signal into the chip. It interrupts the OS. So now when ISR in the OS wakes up, a number of CPU cycles are burned, and then it goes from the I/O driver, which is typically an I2C driver or an SPI driver. It then wakes up the operating system, which then goes back down to the driver and says, oh, what kind of interrupt were you? Was that a sensor interrupt? Was that an error interrupt? Was that a self-test interrupt? Whatever it is. Finally, you get a read request for the interrupt type. It returns the interrupt type. You then analyze the interrupt type, and now you request the data. So from the time the interrupt came to when you request the data, you have all of this CPU cycle. It's a very zigzaggy path. And finally, you get the read request, and at this point here, you actually get the data. So again, to reiterate, to summarize, the interrupt comes here. The first thing you do is ask it, what type of interrupt are you? You then say, oh, I'm the data interrupt. The data comes back, and here we are. Again, 40 years of work, and this is how it is today. Well, now it's time for something completely different. This is the I3C Alice implementation for the touch standard that's been optimized to have the lowest possible latency. And please read the deck to see how these commands interact, but I'll focus on just one key command called touch enable. This touch enable command starts the entire process. So you have a master and a slave. The slave is going to give you data, and this touch enable bit will start the data flowing. The touch enable bit comes, very simple. You write the address, you activate the touch enable bit, and now the data will start. Look at the difference between getting the data and actually getting the interrupt and getting the data. Now the touch slave is ready to report. You touch your mobile phone or your television or your automotive device, and an in-band interrupt is triggered right here. So this first command comes through I3C, and whether you're in SDR mode, DDR mode, TSP mode, it doesn't matter. I3C supports in-band interrupts as part of the base specification. The master acknowledges that interrupt. There's a transition bit, and you get this byte called the mandatory data byte. I'll talk about that in a second, but this mandatory data byte actually tells you what the interrupt is right there. Literally a few bits later, after the master acknowledge, you get an 8-bit MDB, which is mandatory. Now you don't need to go re-request the slave. You don't have to ask it what kind of interrupt it is. It's right there. And then in a private contract, which is part of the standard, the touch data, the sensor data, immediately follows the MDB. So again, to summarize, and I'll say it slowly for translation, number one, the start of the slave sends an in-band interrupt. The master acknowledges it. The slave sends a mandatory data byte containing the interrupt type, followed immediately by the touch data. Again, compare that to this very inefficient process where you have to loop through, ask it, request the data, and get the data. You go from this stage to this stage in three cycles. It's very fast. Then what happens in the touch standard, each touch data report ends in a predetermined frame, and I'll talk about the framing of the data afterwards. And you can keep getting interrupts 1, 2, 3, 4, all the way until the entire touch is reported. Finally, the host will deactivate the touch sensor, and that's the end of the transaction. It's so clean because we're using in-band interrupt. So what are the benefits of this approach? Number one, super low latency. Number two, you've saved the interrupt pin. Number three, bandwidth. You are utilizing the full SDR data rate of I3C. Now, in this next, now this is the second example. Again, this first example was SDR mode. This second example here is a new concept called auto command. Auto command is similar to the SDR command, but it utilizes slightly different properties of the host interface. In auto command, you still have the same concept of touch enable. So you activate touch enable for the slave. But auto command is optimized for the high data rate mode of I3C. In I3C SDR mode, you can get the MDB. That is the only time you can get an in-band interrupt and a mandatory data byte is in SDR mode. Now, if you want to switch up to a faster mode, the old way is you would have to send a series of commands to switch modes. We've invented this new command called auto command, which uses the MDB to indicate that you would like to switch to the faster mode. So again, let's look at this new mode. You get the interrupt, the mandatory data byte. Instead of the data, you get automatically, and there's no gap here, you get a repeated start in I3C SDR, followed by a move this HDR read command. Right here, you enter HDR. All automatically. You don't have to go back to the processor. You don't have to do another software interrupt. You don't have any more transactions with the host and slave. It goes boom, boom, and now you're reading the data here. So again, let me summarize. This is called HDR auto command mode. It is new for the touch standard. In HDR auto command, you receive an in-band interrupt followed by a mandatory data byte, MDB, which tells the slave to switch from SDR to HDR mode, from standard data rate to high data rate mode, with no interaction with the CPU processor. It's all handled at the host level, greatly improving your latency and throughput and power. Let me talk about the touch standard now. The touch standard comprises 4 different documents. At the very top of the document is the first document called the MIPI touch command specification. This MIPI touch command set, or MTCS, is a series of high-level commands that I'll show you later. It's in the presentation, that are good for different lowercase link layer and file layers. It works across. Number 2 is the MIPI touch adaptation layer for I3C, or Alice. This adaptation layer translates the command sets for I3C. If people ask me in the future, could you have an adaptation layer for, say, DPHY or CPHY or USB or some other different link layer? It is theoretically possible. The adaptation layer works with the I3C host interface, which is being discussed. And finally, at the bottom of everything is the I3C MIPI protocol. So 4 different command specifications are integrated together to give you a full command touch protocol. Now, by doing 4 different layers like that, it gives you a very powerful way of manipulating topology of sensors, slaves, and touch devices. Here, this is an example of a very exotic system where you have I2C touch sensors, let's say on the front, mixed with some I3C controllers on the back. This kind of topology is supported by having an abstraction with the 4 different layers. Let's focus just on a simple use case to better understand how the touch control is going to work. In this application, the application processor at the bottom, which is typically something like a MediaTek chip or an Intel chip or a Snapdragon chip, this is where frequently the firmware configuration data is stored. The touch slave device is connected on the actual sensor on the display, and it can have local memory where the firmware is stored. So this is one architecture that's supported. Here, it's very similar, the difference being that the firmware is already stored on the touch slave device. There are 2 different applications that are being serviced here. In this first architecture, this typically lends itself to having a very simple touch slave that's just sensing touch, very low cost, not a lot of processing, typically a voltage analog front end, basic. All of the processing is typically done here on the main processor. That's architecture number 1. Architecture number 2 is a different architecture where you have a sophisticated application. You have all of the touch processing done on the slave itself. The difference between these 2 architectures is the amount of information transferred on the bus. But the good news is the MIPI touch command set will handle both use cases with a unified touch command. So let's look at how that works. You have the operating system on the host side on the left and the touch slave device on the right. The host operating system talks through the MIPI command set. The part that's standardized is here and here and here. Everything here is part of the MIPI interface. As you'll see in a second, these commands are implemented on the slave device and sent through a physical bus. And again, this is a very abstract diagram. This could be I3C or some legacy or some new system like DPHY, CPHY. The nice thing about this model is that we've separated the command set from the low-level link layer interface and the PHY. So let's look at the actual MIPI touch command set. It's very simple. One of the things that we did, and it took us 2 years to go through a very long process with all those companies, Intel, Synaptics, Samsung, Huawei, and Qualcomm, of course, to get us to boil down these commands. Originally, we had many commands. We don't need those commands. We just need 1, 2, 3, 4, 5 commands, and you can do sensor touch data sensing and slave control. The most, and 99% of the time, command that you'll use is called MIPI get touch report. What this command does is simply ask the slave device to provide the touch data. That's all it does. It says, if you have touch data, give it to me. And we'll talk about how that happens. One of the companions to this is that touch enable report that we saw earlier. All of these other 4 commands are simply helper commands. You use them once or never. So out of the entire cycle of the phone, this will be called 99% of the time, 99.99% of the time. This will be called once on initialization. Firmware and configuration data, we have standardized a way to transfer configuration data and firmware from the host to the slave. That is going to be very beneficial because we now have a standard way to interact between a host and a sensor. Right now, we're talking about touch, but you can see how this could be leveraged in the future to sensors in general. Firmware and configuration data, please read the standard. I have some slides on it. We've spent a lot of time between our companies making certain that you can segment the firmware. You can combine the firmware and configuration data into multiple segments. You have automatic segment loading. You have automatic versioning checking. It's very sophisticated and too much for one presentation. I could probably have a whole day on just touch command set. But please be aware that we've done quite a bit of work on the firmware and configuration data initialization process. Self-test and soft reset. Again, we focused on giving manufacturers maximum flexibility. The idea of the MIPI touch command set specification, I keep getting it wrong. It's the MIPI touch command specification, MTCS. The value of it is that it gives lots of flexibility to the manufacturers. We're not taking anything away from innovators. What we're doing is providing a framework for you to innovate within. So these are the registers. So, sorry, I should mention, these are commands sent by the host to the slave. From the host to the slave, the command is command 40, 41, 42, 43, 44. If you put your scope on the bus, you will see these commands flying across. Here, these are a series of registers that you must implement on your touch slave. And this is everything. It's 1, 2, 3, 4, 5, 6, 7, 8 registers. That's it. In these registers, you have very basic, standardized ways to determine which type of interrupt it is. You'll learn what kind of configuration your slave has been placed in. And then the rest of these are all data registers that you would read once at the beginning of configuration. Something like getting the manufacturer information, device version information, command set. These are just diagnostic registers that you can read one time to learn what the status of your device is, what version of the device is. But you don't continuously have to read these ones. The only one that you would read would be set get configuration, and we'll talk about that in a second. Now, one of the questions you may be wondering is how do we organize the touch sensor information to transmit it efficiently with that mandatory data byte? And this is a key concept that we've worked together with those companies to make certain that we have flexibility. There are two different concepts on this slide. The first concept is the idea of a touch report. A touch report is just a series of bytes. That's all it is. We have 6 different types of touch reports, but they're nothing but a series of bytes. And optionally, these bytes can have an enhanced header that tell you what is in the data packet. So the data frame, the size of the data frame is not specified in the standard. The size of that enhanced header packet is 1 single byte. So the overhead of the touch report is only 1 byte, and that byte is optional. If you already know what your sensor data is, let's say it's always 1024 bytes, always, you do not need to waste 1 byte extra. So that's good. And this is especially useful if you have a very powerful sensor that does everything for you, and all you need to do is send the XY coordinates of the touch. So if you only need to send 16 bytes, 12 bytes, why burden yourself with an extra enhanced byte? You don't need it. So that's one option. Number 2, if you cannot send a very long frame of data, let's say 10,000, 15,000 bytes on I3C, you want to have a more organized system, a different system. We also have this concept of microframes. The idea is that instead of sending one big long touch report, you can have a series of microframes that must all be the same size, so you can't have dynamic framing. It's static frame, statically framed. You only need 1 enhanced header, and the frames can come in packet, packet, packet. So each one of those transactions that I showed earlier can be a single microframe. And that allows you to have different applications where you can have microframe data and interruptions between both. Sorry, I said 1 byte. I was wrong. I meant the enhanced headers. It says right there 2 bytes. I was thinking of, you'll see here, the actual description is 1 byte. So we have 1, 2, 3, 4, 5, 6. In fact, the latest draft that we just completed in Bangalore last week, so please do not design to this. We've added a 7th descriptor type to allow for diagnostic and debug data. So let me explain what these types are. Number 1 here, type 0, completely defined by your company. If you do not choose to define anything, you can make the sensor data anything you want the standard is completely silent on that. You can put any data you want there. You can have any packet size. You can have any internal organization you wish, anything. If you were using a more standardized form, there are also HID report types. This is really useful for process touch. This is very traditional in the marketplace right now. And there's the new Linux Android touch report types. Typically, these are architect level 2, the second architect diagram I showed earlier. They'll use these type of reports. Architecture number 1, where you just have an analog front end, it's all going to be raw data. You're going to you won't know what it is, and the standard doesn't enforce what it means. That is just raw sensor data right there. You have a monotonic ID counter that you can read, make sure that you're not dropping frames. This is really only used for diagnostic purposes. We don't expect you to read the frame count every time. If you have to do that, it means you're not saving the data bytes and improving the latency that we talked about on the very first slide. This is a diagnostic tool only. Please do not read this every frame. That is not going to help. And finally, the size of the report is available as well. So I'll just briefly glance over this part of the slide. Again, we have standardized how to reset the slave. You turn on the power on, you power on the reset. The slave initializes itself. It tells it loads what kind of manufacturer it is, what revision it is, what version of the firmware it is. And as you'll see in the deck and in the standard, this information is used to determine if you need to update the firmware. So that's obvious. You load the firmware, you load the configuration data. And again, what is configuration data? Initially, we had defined all sorts of calibration, thermal feedback, all sorts of things very specific to touch. We've removed all of that from the standard. Configuration data is anything you want it to be, which is not firmware. It's very flexible. Typically, it is used as calibration data from thermal testing or factory calibration to make sure the sensors are all working correctly. That's a typical use case, but I'd like to again reemphasize that is not required in the standard. Once you've loaded all of this, you update the firmware register, obviously, because you've just updated the firmware, and this one bit tells you, are you ready for operation? So the slave will initialize itself and interrupt the host saying, I'm ready for operation. Once it's sent that interrupt, then all the slave has to do is activate that touch enable bit and it will start sending data. That is the entire process. So please, that's the end of the command set portion. The actual details of the spec you'll have to download from the MIPI standard once it's published if you're not already a member. The details are long and complicated, but I would like to focus in the remaining couple of minutes here on the lower parts of the standard. What is supported? Well, we have 4 different profiles here. You can use it with a legacy profile. So there's absolutely the support to do that currently today with what you have. You can build touch products today with I2C. Of course, you'll have to use an out-of-band interrupt. Of course, you'll still need a reset. But it will work. The preferred implementation is with the new I3C standard and with new sensors and with new touch devices. You have standard data rate profiles optimized for sophisticated processing. But if you need the extra speed, we highly recommend you implement a DDR sensor, a double data rate sensor. And if you really need the high performance, a TSP or TSL sensor. Again, I'm not going through this table. Please look at the different profiles. The key thing to realize is that in all of these I3C profiles, mandatory data byte is required, and you will have the access to the very fast, low latency modes. So just to wrap up my talk, I'd like just to re-emphasize this is the old way of doing it. You've burned a pin that is only used at the kilohertz range. This pin will trigger maybe at the 100 kilohertz, 200 kilohertz, whatever the line rate of your sensor is, typically far below hundreds of kilohertz. But you've burned an entire pin on that. Number 2, you've this interrupt comes in, it wakes up the OS, countless cycles are burned through this loop, determining here at this point, what is the interrupt? You've burned all of this time. Finally, you now get the data here at the end. This is the traditional legacy way of doing it. And this new way of doing it, I'll just show you quickly here, uses this mandatory data byte concept. The mandatory data byte immediately tells you the type of interrupt and immediately gives you the data. Huge savings. And in the last 15 seconds before they pull me off the stage here, I just want to show you what the mandatory data byte looks like. The mandatory data byte here is very simple. It has one bit to tell you whether you're in that auto command mode, so whether you're in SDR or you need to switch up to the high data rate. And then right here, these bit fields match the exact interrupt type that you need. It's in the standard. So I have my Chinese to English translation kit with me as well, and I'd be happy to take any standard questions on this, or please approach me afterwards. So that's the end of my talk. Again, thank you for being here for the very first presentation on the new MIPI Touch standard. I've been working on this for 2.5 years. I feel very close to it, and so if I'm talking longer than my time allows, it's because I'm very passionate about this subject. Thank you very much. Are there any questions in Chinese or English? Okay, very good. Thank you.